So good afternoon again. Welcome. I'm Valentin Popescu. I'm from Artel Innovate, and I will be your host for today's session. This lecture brings together leading experts who will share their insights on critical components for the future of 6G networks. Before we begin, I'd like to share a few housekeeping rules for our meeting today. This session is being recorded and will be published on the 16G website for future reference. Feel free to post your questions and comments in the chat. I'm sure that our speakers will address them after their presentation or in the Q&A session. We encourage you to join our discussions using the hashtag 16G Open Lectures on social media, and please also tag us 16G Global. And if you encounter any technical issues, please contact us directly in the chat. Without further delay, we will begin our event. And I would like to give the floor to our first speaker. It's Arian Kaushik, Associate Professor in Manchester, and he will outline what to expect from electromagnetic signal and information theory. Arian, if you can hear us.
Hi, Valentin. Yes, I can hear you. Yeah.
So
Hello.
you have the floor. If you could share your screen, and we'll let you know if everything is fine.
Yeah, perfect. Thank you. So here, I think I might require.
Yes.
Yeah. Okay. That's great. So I think it's visible, right? I think there are too many windows.
Let me stop sharing my screen, and now you should be able to share.
Okay. Now, is it visible at the moment?
No, at the moment, no.
Right. Yeah, I'm not sure. I think why it.
Arian, this is Marco. I can see it. I think that I can see it. I can see something.
Can Valentine see it? No, from their side.
I don't see it, but
is all other participants can see. I'm not sure if it's just one screen problem or is like everyone cannot see. I'm not sure.
Can you try to go to the next slides just in case to see whether we are seeing the correct? Yeah, I can see.
Yes, I can also see it.
Yeah, I can see
okay,
it. Yes.
Perfect. That's okay. Maybe I can start presenting.
Yes, please.
Okay, thank you, everyone. So again, thanks to Valentine for moderating our lecture today, the 16G lecture. So basically, this is a new technology. I mean, it's not so new, but it's of course with the amalgamation of different technologies, it's quite a new concept as far as 6G is concerned. So basically, to get into the topic right away, because we don't have too much time. So just to give some introductory sort of background on what we actually had been expecting with our sort of 5G services, as we see that the subscriptions for 5G are actually estimated to reach about 6.3 billion by 2030. So this is quite a large number. So compared to, let's say, our previous standards. So the expectancy is that the whole world population coverage for 5G is actually going to outgrow the sort of previous generation standards that we have had, the previous generation services that we have had when it comes to 5G. And 5G is basically expected to carry about 80% of the mobile data traffic by 2030. This is again a large amount of the whole sort of networking infrastructure, communication infrastructure that we have. And there are like a lot of worldwide efforts that have been happening, to advance 5G. So basically, we were sticking to these three key usage scenarios of enhanced mobile broadband, massive machine type communication, ultra reliable low latency communication. So we are basically advancing this over further, and sort of trying to roll out the 5G advanced base services in next few years. When actually 6G comes into picture, we do see that we are taking forward the 5G and 5G advanced sort of features, the key user scenarios, and we are also adding on top some enhanced capabilities. So basically, we are adding integration of sensing and communication. So try to make our systems and networks more multifunctional, so that we can save the hardware resources, we can save the spectral resources as well. So basically, try to use the same frequencies for dual operation. So basically, having sensing and communication at single frequency, and at the same hardware as well, because the beamform that you're going to use is carrying both information of sensing and communication. Then you have integration of AI and communication. So basically trying to utilize automated approaches, AI models, machine learning methods, deep learning, many up and coming techniques for communication, wireless communication, or even in many cases, wired communication too. And also trying to use communication for AI as well, right? So basically trying to say, let's say over-the-air computation or some other similar techniques to use communication fundamentals to enable AI. And then the third one is ubiquitous connectivity. So basically to provide anytime, anywhere, anything sort of connectivity. So to add up, basically integrate your terrestrial network, your ground network with your non-terrestrial entity. So try to really be connected all the time. So really connecting the unconnected in many cases, and also for providing massive connectivity as well. It is one of the key solutions that have been considered. And these things, they lead to many different use cases, applications, and so on. So in smart healthcare, remote surgery, smart homes, indoor application, any outdoor application, and so on, holographic communication, robotics, or some sort of agriculture, semantic communication. Many of these use cases and applications they come across when we talk about the IMT 2030, the 6G framework that we're talking about. And also we do see that as well, this is being pictured into our standards as well. So how we have been actually evolving in all of our standards, right? So 3GPP release 17 was concluded recently. So basically you can actually see that all these technologies that we're talking about, so there is sort of a trajectory that is kind of moving forward. So with latest releases of release 18 and 19 as well of 3GPP, we're trying to include ISAC based joint system design for sensing and comms, and also trying to play around with the MIMO solutions, massive MIMO solutions, and so on, right? So we can see that how we have actually evolved quite a lot in last decade or so, right? In the last 2 decades, as you can see here in the sort of this chart as well, right? So the main idea is that when we are moving towards 6G and perhaps even beyond, is that we are trying to move forward from this triangular framework that we have had, and try to provide more enhanced capabilities to our systems and networks. So that's the key idea, is not just having communication, but going beyond communications. As I was also mentioning, that basically you can come up with different solutions and so on. But if I have to point out a couple of main key usage scenarios, or the key areas of work that have been happening in 3GPP release 18 and 19. So you have next generation MIMO solutions, high mobility scenarios as well. So especially in the cases of vehicular communication, or when you have the non-terrestrial networks, right? So in all these cases, when there is a lot of handoff of services, then you need to consider these to enable these high mobility scenarios as well. Then trying to use AI machine learning methods or any sort of optimizations of our network, of our automated algorithms that we're trying to build for, especially for the applications of next generation radio access network or open radio access network as well. Having extended reality, and also trying to have energy efficient architectures as well. This is something that we were missing on big when it was about 5G. Then you have non-terrestrial networks as well, which has been continued since last releases of 3GPP. Then the addition is also now because of the joint design of sensing communication and many early study items that have been also being considered for these scenarios. At the same time, we also need to remember is how we are actually evolving, with our 6G standards, with our 6G objectives that we have had. And it also depends on, what kind of resources we have with us, right? So in this scenario, what we are aiming for is to basically use something that we are already aware of, or something is familiar to us, right? So basically not to move too much away from the microwave spectrum to roll out the 6G services, to basically, consider somewhere closer to our sub 6 gigahertz frequency, so about 7, 8, 9 gigahertz sort of band. So we're considering centimeter wave, right, as one of the key enabling spectrums for 6G services. And also we see that there are already some existing applications. We see in X-band about 8 to 10 to 12 gigahertz. We are already using radars for, let's say, weather monitoring, air traffic control, maritime security, and many other sort of applications. And in some geographical locations, we may also require high frequency solutions, let's say sub-terahertz based things, right? So about 90 gigahertz sort of frequencies. So we also see there are existing applications, let's say in automotive radar at about 77, 80 gigahertz. So the idea is that even if you want to implement, let's say, sensing comes together or any solution like that, it is also sort of deployable at these frequencies that we're actually considering. And in this particular paper, we also try to do some experimental work with our colleagues. So feel free to check through that as well. It's quite a new sort of work we try to consider for, in relation to the frequency spectrum that we can use and how different technologies can play around, right? And multiple scenarios you can come up with. So all these, vehicular scenarios or any sort of 6G objectives that we were considering, all the use cases applications I had in that circular figure. So they all can be explored actually at many of these, different frequency bands and so on. So basically coming to also the topic is that because we also need to consider is that we are talking about sort of ubiquitous intelligence as well, right? When it comes to the 6G framework. So how does it come? So it's a combination of different technologies, right? So first we actually start with something what is called electromagnetic signal and information theory. So what we have is we combine our electromagnetic wave theory with signal processing and information theory, right? So what it means is that let's say when you have mathematical, let's say Maxwell equations and so on, right? So you want to actually make these equations easier to solve. So in these scenarios, you use some probabilistic models to basically try to solve them in a much sort of easier way, right? And you also use some sort of intelligent signal processing approaches. So signal processing would be basically your, related to your compressed sensing and trying to also come up with very good optimization solutions, right? So the idea is that you build a system which actually utilizes principles from different fields all together, and for basically the sort of combined benefits that we have. So it can lead us to, let's say, very good applications and sort of, new antenna designs. You can have like different beamforming approaches as well. So you have hybrid beamforming, right? So basically you are using, digital precoding and baseband precoding as well. Now you can also add another layer of, let's say, if you're trying to use meta surfaces, right? Or any sort of spherical wave modeling, or let's say any sort of, you want to use continuous aperture in case of holographic MIMO, let's say, if you want to have the holographic output, right? So you can actually end up with some sort of tri-hybrid beamforming as well, right? And you can also, have channel modeling based sort of solutions when you try to explore these ideas. And the main idea is also to have low complexity solutions. So to achieve highest capacity possible, it can come through your, intelligent sort of optimization approaches. It can come through how you actually also, use the beamforming, right, next to your antennas, what kind of meta surfaces you're also going to use. So I will also discuss different variants in some later slides as well. And are you also considering sort of hybrid scenarios of far field and near field, or you're focusing more or less on the near field scenarios or just far field scenarios? So depending on really your application, so we can explore the concept of ESIT. So this is basically a new term, but it's kind of, evolving with, as we proceed with all these electromagnetically consistent models and many other sort of solutions as we see in our literature recently, right? So in this framework, so the particular thing I wanted to touch was about the intelligent meta surfaces, right? So, I mean, our colleagues will also discuss, some of these techniques, how you can use some sort of dynamic arrays of these meta surfaces, how we can use, let's say, different stacks of these. Right. So the basic idea, I mean, when meta surfaces started, was that you have a large sort of mirror-like surface. So let's say if you throw in some sort of beam there and you want to actually reflect that and send it towards the intended direction of your end user. So you could do that using this large surface, right? So this was actually passive in nature. So there were like some early experiments, in industry as well, and even before, like in 2019 and so on. So the idea was to actually provide some sort of buffering to your signal. So when you want to especially reach larger distances, and also when you're especially operating at very high frequencies, right? So where you have these path loss effects or some distortions, right? As in the case of millimeter wave or sub-terahertz and so on. So this proved to be very useful sort of technology there. And you also see that they were mostly considered to be passive in nature, is that you're not applying any sort of amplification or something like that. But actually, if you require amplification, you can actually, use this reflection type amplifiers as well. So basically, you actually call them active reconfigurable intelligence surfaces. So basically, you also want to reach even larger distances, right? That was the principle of active risk. And you can also have some sort of trade-off between energy and sort of how many degrees of freedom that you have as well. Then many other variants came later on. So you have star risk as well. Then you have the stacked metasurfaces. So stacked intelligent metasurfaces generally, also our colleague Marco will talk about this in detail later. Is the idea is, is inspired by, let's say, our deep neural network sort of analogy that we have. So basically, you have multiple layers, multiple stacks of these meta surfaces, these basically large array of these surfaces, because the idea is that you want to increase the degrees of freedom, increase the capacity. And then there is another, mathematical issues and so on, how close they should be, how narrow should be the sort of distance between these, or how many of these you can use and so on. So hopefully by end of this lecture, you will actually understand several of these aspects as well. And we can also try to explore different other variants based on, let's say, OFDM principle. Let's say in the case of metaprism, and you're trying to use different frequencies as well to use what kind of metasurface, which metasurface you are going to use, right? So different sort of theories and sort of practical experiments are also going ahead when we talk about this ESIT framework, and in particular the metasurfaces belonging to this framework, right? So in this framework, in this idea, recently we have also come up with this group, this initiative, so which is called the Electromagnetic Signal Information Theory ETI group. So Emerging Technology Initiative under IEEE ComSoc. So this is being chaired by myself, Marco, and also Ling Long as well, and many of our colleagues who are actually a big part of our big team, right? So there are about like 100 experts from all the fields. So the idea was to have all the experts from different subfields, right? So you have people from antenna theory, electromagnetic wave theory, you have people from information theory and signal processing as well. So all these guys bring on all the biggest sort of expertise to basically take the technology forward. And we are also writing some books as well. So basically editing some books. Marco and myself are also editing one. And I myself also solely editing another one. So this is one is on the electromagnetic signal information theory, the key concepts, and also try to discuss some background and sort of future trends as well, and some standards inputs as well. Because this is, again, it's a very evolving technology. We still have yet to see a lot of improvement, a lot of sort of scope that we have actually in this technology. Then I'm also writing and editing basically on intelligent metasurfaces as well, and to discuss what kind of recent advancement in terms of what kind of variance it can have. So let's say you can have your holographic MIMO, you can have your, let's say any sort of new generation, next generation MIMO technologies as well, right? In terms of stacked metasurfaces, you also have flexible metasurfaces. You have many other sort of variants that is also being discussed in this particular book, and they will be out soon in some time. Going a little bit more inside into the topic of these metasurfaces, let's say if we pick reconfigurable intelligent surface as, let's say, the proof of concept, let's say if you want to use this kind of metasurface, again, I mean, all these technologies that we try to plug in and try to incorporate with other technologies, we can actually try to replace the variant. So let's say instead of RIS, you might be able to use star RIS, you might be able to use SIM, or your flexible intelligent metasurfaces, and you see the sort of trends and the results and so on. So here in this particular paper that we published in IEEE Comms magazine, so we try to come up with some sort of new framework where we combine index modulation with intelligent metasurface, with reconfigured intelligent metasurface. So the idea here is that you don't really have to use the whole large surface that you have. You can actually use some of the unit cells of these large surface, right? And you basically do not even require the successive interference cancellation unit. You don't need to filter out the signals at the receiver, because you already embed the information in a way at the transmitter that you don't really require this sort of decoding when you actually reach the receiver, as is the case with, let's say, the other multiple access approaches or the frameworks that there are, right? In NOMA or splitting multiple access, or some other sort of multiple access approaches as well. So if you're really interested into knowing how we can play around with this kind of framework where we use some sort of diversity, let's say it can be in terms of antennas, it can be in terms of your let's say frequency, it can be also in terms of your polarization as well. So different diversities that you can explore when you talk about index modulation, right? So how you embed your information in different ways, what kind of combinations you have in the code words when you're actually doing the transmission. So that is something very interesting that we try to present in this particular paper. And then we can also take further this idea. So basically you can come up with better mathematics, you can come up with really different diversity explorations and so on when you combine these technologies together. So again, this is quite a good topic when it comes to exploring the intelligent meta surfaces and also trying to explore this with index modulation. So this gives you, very good degrees of freedom and several other sort of diversities that we are talking about to basically involve in your communication of your signal. But there are still many open issues and research directions that we can think of here. So, again, how would you model your channel or estimate your channel as well? How you design the precoding or beamforming? So do you need to optimize these RF chains? Do you need to optimize these quantization units? Can we make it more energy efficient than it already is? Can we, not just use passive risk? Maybe we try to explore the active risk sort of variant. And, many things, how we actually also use index modulation as well together with all these different variants, right? So this is also something that should be explored. So different scenarios we also try to address in some of our papers, but again, a lot of research is needed in all these sort of open issues and these directions that I've just mentioned. Just some quick points, right? And we can also try to explore, let's say, these kind of scenarios of using, meta surfaces, but let's say if we come up with some sort of reconfigurable refractive surfaces, and also especially in near field scenarios, we can also enable a good, sort of this tri-hybrid beamforming sort of design as we were discussing, right? So earlier, so basically you have your digital precoder, your baseband precoding, you have your analog precoding, all these phase shifters, and actually you have your sort of antennas as well, and your basically your meta surfaces as the third sort of beamforming aspect, right? So you can explore this in a refractive way as well. So if you're really interested, so because time is quite short, so I will just go very quick through it. If you're interested, please feel free to read through this paper. Also, we have provided a preprint as well for this particular work. And you can also combine these technologies again with different other technologies. So let's say ESIT was one of the important technologies, as I discussed in the beginning of my lecture. So you can also combine these intelligent meta surfaces with ESIT signal as well. So you have a dual functional signal, right? Instead of sending just, let's say, communication signal, you're actually carrying this information of both communication. Also, if you want to, let's say, detect any targets, objects, and so on. So you are basically able to perform these optimizations that I was talking about together with this dual function signal as well. And then you can see the trade-off between sensing communication. Sometimes one of the performance gets dominant, the other performance is not that dominant, depending on how much weighting you give to each operation, right? And then on the same frame, you can also explore the unit cells sort of optimization. So you might use not the whole large surface, but you can use just some bits of it as well. So that is also something we try to explore in this area of research. And you can also combine these with non-terrestrial networks. So basically, if you really want to mount your meta surfaces on drones or on satellites, or when you want to really reach larger distances and you want to explore high frequencies, as I was mentioning earlier, or different other scenarios as well, you can plug in all these different variants of meta surfaces on these applications that I was discussing about. So in particular, you can also combine this with non-terrestrial networks as well when you have these non-terrestrial entities integration with your terrestrial network, right? And the same thing continuing with that, I mean, they synergize very well. So basically you can put them, let's say, on a wall, on the maybe roof of a building, or you can actually mount them on the moving platform, the flying platform that you have, the drone or the UAV, the swarms of UAVs, or you can have any, balloons or dead balloons and so on, right? Or you can mount them on your satellites as well, and you can basically reach larger distances. So it synergizes quite well when you combine all these technologies together. And we discuss these sort of overviews and standards sort of updates and so on in multiple of our papers, right? This is also important. Why? I mean, this one slide, a very quick one, because we can also explore these kind of scenarios for, like disaster management, public safety, because this is one of the important use cases that we are considering, right? To use it for public safety, search and rescue operations. So when, let's say, infrastructure is actually broken, the one that was actually usually used, in those scenarios, you can send in your drones, or you can have a direct access from your satellite. You can actually be able to provide connectivity then in the cases when the infrastructure is actually broken. You can basically use these flying platforms to relay some information to some other control center unit or base station that can actually monitor the situation or manage the sort of disaster affected area. And in this scenario, again, when you combine these meta surfaces with non-trusted networks, you can also come up with some ideas where not only you're designing the antennas or the beamforming, basically you're also trying to explore the concept of movable antenna arrays, or let's say the fluid antenna systems as well. So basically here, even your medium can be fluid, right? So if you want to know more about this, again, please feel free to go through this paper available on the preprint. But my main idea was to pitch that you can also combine different technologies together, and you can come up with like sort of new solutions and new aspects of these the things that are falling under the framework of ESIT. And you can combine with this with ISAC also, so not just non-trusted networks and meta surfaces, and not just with some technologies like fluid antenna systems. You can also combine this with ISAC as well. And at the end, you might end up with a very expensive system where you utilize this, again, for, let's say, public safety application. We're trying to explore all these combinations of using a dual function signal, reflecting that using the meta surfaces, and also mounting these meta surfaces on your satellites or on your stationary objects on the ground and so on, to basically take control of the situation. So that you can actually do. And in the addition, you can also use some AI solutions as well for resource optimization or some resource allocation. You can try to combine, this mobile edge computing, edge cloud computing as well. Different tier network architecture you can use to basically check which, sort of computing or communication resources you require, and so on. Many things that we talk about, but you can actually come up with a picture as well, is where you actually have the combination of all these scenarios. And you can also expand this, let's say, for some other latest applications. So let's say here we also try to use some sort of quantum-aided, communication. So you have the quantum processing, you have the intelligent meta surfaces. You're trying to combine AI method as well. So in particular, deep reinforcement learning for the direction of arrival estimation accuracy that you will have. And basically, the signal that you're using is not just communication signal; it's a sensing comp signal. So we take into account several of these aspects together in this particular paper. It's recently published in IEEE JSAC. So it's a quite extended paper, quite lengthy paper. So if you really are interested into checking these recent advancements, so I really suggest to also go through this paper to check like how different technologies can be combined together, and also with some sort of extended mathematics that we present in this particular paper. So again, I mean, many conclusions as well were there, so I will skip that. And then we also have, several publications as well. So please feel free to go to any of these, and we also run a podcast series as well at the end. So again, we're discussing about different, aspects of different technologies of 6G. In particular, I mean, we have also discussed on the framework of ESIT very recently. So with Marco, we recorded a podcast. With Davide, we had done one in the past on these meta surfaces, and also with Marco as well. Again, we had recorded another podcast a long time ago when we started the series. With Kit as well, we have done a podcast on fluid antenna systems. So quite useful resources if you're very interested into knowing more about these technologies and hear from all of our colleagues. So this is also a good point to check. So with this, thank you so much. I hope I haven't taken too much time, but after the lecture, we can also take questions. So if you would like to pose any question now, that is also fine. But if you also want to wait until the end, please feel free to ask, or you can also email me anytime, any question, and I'm happy to answer that. Thank you.
Thank you very much, Ariane, for this presentation. Let's see if there are any questions. If not, I would just like to give the floor to Marco Di Renzo.
Yes. Hello, everyone.
Hello.
Okay, let me share.
Yes, we can see your presentation.
Okay. All right. So thank you very much. Yes, we have more or less 20 minutes or so. Thank you very much, everyone, for organizing this and for having me. So I'm glad to be part of this online lecture. So the scope of my presentation will be focused on the use of metamaterials for wireless communications, and essentially the role that these metamaterials may play in the context of electromagnetic signal information theory, and also how they may be utilized for a new implementation of machine learning in the RF domain, in the analog domain. So now the idea is the following. I will briefly recap what has been happening over the last few years around a concept which is called smart radio environments, which essentially means how to use metamaterials for wireless applications. And then I will go through the emerging concept of deep diffractive radio, or essentially wireless systems that capitalizes on advanced metamaterial structures that mimic kind of machine learning algorithms. Okay, that's just to give you an idea. As you can see from this figure here, it's a quite interdisciplinary field which puts together different disciplines, including metamaterials, electromagnetic computing, and neural networks. And this is a joint work, most of the things that I will tell you with another speaker, Chao Wen, who will speak next after me. So now, for those of you who are not familiar, just really 5 minutes less of a recap on what these metasurfaces or reconfigurable metasurfaces are. So essentially, we have a large surface which looks like a planar array. We have electronic circuits that allows us to change the response of this device, so it's not completely passive. But as we will see, we would like primarily to keep the complexity very low, so not to have a power amplifiers, etc. And we have a tiny antenna elements that allows us to basically take the signal that comes in, that illuminates the device, and then that is scattered in the environment. The objective is how to finally tune all these elements to achieve some target, some objective. So now the concept of smart grid environments over the last few years has mainly been focused on this. So putting these devices on objects, which can be wall or near transmitters and receivers, and then illuminates this device with some waves, and then try to control the reflections or the transmitted signal of this surface. And the idea is that if you can finally change the response of each element that I showed you in the previous slides by optimizing the electronic circuits, you could change for example, direction of reflection, where you want to direct the signal, but you could also null the signal in directions where you don't want that the signal goes. Okay, for example, because there is an eavesdropper. So the mathematical background is centered upon the concept of Snell law, or generalized Snell law. Okay. So now there are many papers, so I really not gonna go through all of them. Marianne showed you already quite a few. I just want to show you that besides these research papers, there are also some experimental activities and system level studies that have tried to evaluate the pros and cons of this technology. So one of the earliest research works in this field was done jointly with Huawei, where basically thanks to Huawei Sweden, where thanks to a simulator, a system level simulator, we implemented an RIS model into this simulator, and then we analyzed the coverage in a given area without and with the surfaces. And here you can see, for example, that a millimeter wave without using surfaces, less than 50% of the users are in coverage, which means that they get a signal that we judge sufficient for communications, high quality data transmission. If you deploy a sufficiently large number of surfaces, the reliability of the coverage of your signal could increase to 95. Okay, this is under relatively realistic conditions. More recently, we collaborated with China Mobile in order to see what is going to happen if we utilize the typical parameters that are utilized in 3GPP for evaluating new technologies. So we considered basically the specs that are available in 3GPP documents, and we obtained that by deploying these surfaces, so your reliability increases of about 4 to 7 dB, which is quite significant, especially because these results are obtained for surfaces that are not extremely large. So it was relatively realistic. And then, I mean, with other with another company, Citadel, we try to see what is going to happen if we consider a private network, which in this case was an industrial setting, and we could deploy these surfaces and try to figure out how the coverage could be improved without deploying additional base stations or active devices. And so we upgraded the ray tracing module that they have, which did not include RIS, and we calibrated the models through measurements. And the results show that, I mean, we got quite a good match. And then the results also show that you can get quite a good improvement in terms of coverage if you can deploy these devices and optimize them. So more or less, I mean, there have been some, positive results, even though, of course, there are some challenges that I will try also to tell you in a couple of slides. So now, if you are interested in what is happening in terms of industrial interest, there is an ISG group within the ESIT focused on this technology. So you can go to the website and you will find all the documents that have been published so far. Yeah. So now we learned a few things about this technology, pros and cons. One of the things that we like, but there are challenges, is that this technology operates in the RF domain, and especially we don't use power amplifiers, we don't use digital signal processing, we don't have RF chains. So the complexity is very low in principle compared to other technologies like active base stations, active repeaters, relays, etc. But this comes with challenges because if you don't have a power amplifier, your range is limited. So you need to have a large surface, or you need to ensure localized coverage. If you don't do digital signal processing, your capability of manipulating the signals might be limited. And I will address this point later on with an advanced technology. And if you don't have RF chains and power amplifiers, and you cannot decode the signal because you don't have digital signal processing, you cannot transmit and decode the pilot's signals for channel estimation. So you need to develop smart enough techniques to estimate the channel and to reconfigure the surface in an efficient way. And here I will show you in the very last part, very briefly, that integrating sensing into the surface may allow you to solve some of these problems. Okay, so there are pros and cons in these features, let's say. Now, but we understood one thing, that maybe we could avoid to do some of the functions that we were used to do in the digital domain and through different blocks like beamforming, decoding, demodulation, etc. We could do everything in the RF domain, in the analog domain, significantly simplifying the computation, the complexity, and also reducing the latency. So the sort of from digital-based radios or all digital radios to wave domain radios. So radios that operate in part or predominantly in the analog domain. This has also challenged the deployment of these surfaces, some of the models that we utilize for wireless communications. And here is where electromagnetic signal and information theory kicks in, because as I told you, you don't have a power amplifier, so you need to exploit the size, the aperture of this device to reach good distances. And so if you start deploying in an indoor environment, for example, a large surface of 1 square meter, 2 square meters, you may easily be in the near field where the waves are not planar, but are spherical. So we need to update our models and also to utilize different techniques. There are advantages in if we can have a spherical waveform. For example, the possibility of focusing the signals at very localized spot. But it comes also with challenges, and in any case, we need to update the models. Another thing is that usually these devices are designed not in this way, not as conventional antennas, where the elements are spaced lambda/2, and where usually the electromagnetic mutual coupling can be ignored to some extent, but they are usually built in this way, where you have a very dense deployment of elements for different reasons. Reason number one is because you can manipulate the waves much better, and you can achieve functionalities and efficiency that you cannot achieve like that. For example, very large deflections in terms of reflections, the angle of reflection. But also, when you have 1 square meter or 2 square meters, you really want to utilize all the area, so such that the effective area is actually the physical area. Also, because the more the elements you put, the more the beamforming gain. Okay, so this also pushes us to rethink the communication models, because we need to consider the mutual coupling, and we need to exploit the mutual coupling if we want to get any gains from this structure, which makes things more complex, and also we need to use different models. So for all these reasons, at some point we understood that while we have been designing wireless systems primarily utilizing a mathematical-based approach, is information theory, which is very good and has allowed us to really understand the fundamentals, and it will stay there. But maybe we need to complement or try to reintroduce in this information theoretic framework more physics-inspired, physics-compliant, electromagnetic compliant models. And here, I mean, there are different approaches. One, it would be very, I mean, it's very fundamental, but it might be a little bit complex for, at least, I mean, for us, really moving directly from Maxwell equations, or we can try a compromise by bridging this complexity between pure electromagnetic theory and information theory by using a circuit-based approach. And there are now a few papers focused on that. But it's really the synergy between these three and more disciplines that it seems to be needed. And this is essentially a little bit the message that was summarized to the best of my understanding in this paper in 1953, where possibly we could enlarge basically our tool set from a pure IT-based approach to a physics-based approach to communications. And there, I mean, that's one of the papers where we discuss all these things. So if you are interested, you basically can have a look. So now, here today in the second part, I would like to go to more advanced metamaterial-based structures that may allow us to do better processing and at the same time to solve some of the issues of single-layer devices. So very quickly, in 10 minutes, I will try to tell you what the concept is, and I will try to show you a few results and give you some pointers and possibly opportunities for research. So now the main idea is that we know how powerful this deep neural network could be in terms of inference and processing, but we also know that they are now predominantly built and conceived by processing signals in the digital domain, which comes at a high flexibility, but also at a very high cost, because the digital signal processing units, the power consumption, as we will see, may increase, I mean, exponentially or significantly with the number of bits that we utilize. So one idea would be, can we do the same if we were staying in the wave domain, so without doing this analog to digital conversions, motivated by the performance that we obtained by utilizing RIS. Okay. So now I don't have really time to give you throughout the literature, I mean 100%, but I want to give you three pointers to tell you that this idea has been there also in different communities, and now we are trying to see what we can do in the wireless field. So this is one paper published in Science in 2018, whether this idea of building a machine learning module in the optical domain to mimic a deep neural network was studied. This was not reconfigurable. It was static, so it means that you implement it once and then you cannot change the functionality. Okay. Also, one of the assumptions is that here there were not non-linearities, so all the processing was done linearly. Now there are people that are trying to overcome these limitations, but without going much into the details, another paper that was published in that year, 2018, was this one from Christophe Callot, who is an expert also in metamaterials. And in this paper, the idea was this: if I want to do something very complex, I could do this with only one layer, but this might be too expensive. And I will show you an example where I may split this functionality, this complex functionality, into simpler functionalities that are executed by multiple layers that are stacked one after the other. Okay. And this is basically the concept that I want to convey, which mimics, which resembles a deep neural network. The layers really resembles these layers of a machine learning scheme, DNN scheme. Then, 3 years later, there was this group from Tiejun Chui that built this multi-layer device and made it reconfigurable. Okay, but this was reconfigurable with some power amplification. So it was very powerful from the processing point of view. If you see the papers, they were able to do machine learning inference, but they were modulating the amplitude also of the signal. Okay. So now, if you want to know more about this, I recommend you to have a look at this couple of papers where there are quite interesting discussions about the role of optical computing and also the role of metamaterials in this context. Let me emphasize that it's not only optical in the optical domain. There are now quite a few papers at frequencies that are of interest for us, okay, for our community. So now, then a couple of years ago, with Chao, who is also in this part of this lecture, and Jian Chen, MR1. Jian Chen is a postdoc in the Chao group. We started looking at this multi-layer technology in an attempt to make it as simple as possible without using power amplifiers as RIS, but capitalizing on the multi-layer and see what we could do in this context. Okay. So this is the paper where you may want to have a look to the idea, and now there are quite a few more. So now the idea is simple. We can have multiple layers of metamaterials which are put in a vacuum container. And then when the signal propagates from one layer to another, we do the processing thanks to the scattering elements and the electronic circuits, which can be optimized for the purpose that we need, for what we need to do. Now, for those of you who are focused on RIS or are familiar with RIS, this is not a device that works in a reflection primarily, but it works in a refraction. So the signal goes through the device from one layer to another. Okay. You could also build the first layer to be reflective and refractive at the same time. This is called the star RIS, for those of you who are familiar with this field. So the similarity is clear, I guess. So the scattering elements plays the role of unit cells. That's essentially the scattering elements plays the role of neurons in a conventional machine learning technique. And so the key features are that we do everything in the wave domain, so we can reduce complexity and reduce the power consumption. We can enjoy the massive computing capabilities of machine learning and inference capabilities thanks to the multi-layer structure. And this could be a multifunction platform because thanks to the multi-layers, we can do much more than just reflecting signals, as I will show you in the next few slides. And we could also put together different functions, communication, sensing, and others. Now, let me show you quickly a couple of just four examples, and then I will wrap up. So one of the functionalities that we studied is to replace digital beamforming at the base stations by doing this beamforming in the analog domain. So the idea is that you could remove this block and then to use a simple DACs, and then you do the processing when the signal leaves from the antennas. These antennas could also be coplanar with the first layer. Okay. So what are the advantages? The advantages is that in principle, in terms of scaling laws, then I mean the actual law, it really is technology dependent. So there are many discussions here, but at least in terms of scaling law, the power consumption of analog to digital converters grows linearly with the bandwidth and exponentially with the number of bits. So if you are thinking of deploying this at very high frequencies, and you may want to use this technology because this allows you at the same time not to consume that much, but also try to reduce the number of bits that you need. And there have been a lot of works in millimeter wave, for example, in utilizing 1 bit analog to digital converters for these same reasons. Here we are trying to capitalize the processing capabilities in the wave domain. Okay. The second example is to show you how this multi-layer can allow you to focus the signal quite well, which is a complex function to be done. So imagine that you have an area and you want to focus the signal in this way. Okay, this could be a street where you want to make sure that the signal is only there, but there is no signal elsewhere. Well, this is what you can get with only one surface, very simple, where the unit cells can only introduce binary phase shifts. So very simple, but there are test beds. I will show you one in a few slides. So you cannot really achieve this kind of granularity. If you add 3 surfaces, you can do slightly better. 5, you keep increasing, and then I mean with 7, you almost get to the to really what you really want. Then there is a diminishing return law, because also the more the layers, the more the scattering losses that you are going to have in practice. So there is a kind of optimum in terms of number of layers that you can utilize. The third example is goes in the context of what is known as beyond diagonal RIS. So you may, for those of you who are working on that, I think you may have seen the papers from Bruno Clerc from Imperial. So the idea is in the typical model that we use for this device is extremely simple, at least for us wireless people. We assume that each element is controlled independently in this way. So assume that the one reconfigurable element is a wire antenna. We control through a circuit each antenna independently from the others. And this mathematically gives us this diagonal model. Okay. But the optimum, from the information theory point of view, if we really want to manipulate the waves in the best possible way, we should take into account the interactions between the elements, which are packed in this device, through additional electronic circuits, which allows us to control the interaction. Okay, so your model is not anymore a diagonal, but is non-diagonal, which makes things much more complex to be implemented. I mean, we get better performance at an higher complexity, which is expected. So there is a trade-off. So here, this multi-layer structure may be helpful considering the view of Callot paper, Christophe Callot paper, because if you have multiple layers and these layers are diagonal, so you have a diagonal response, when you put them in a cascade, you have a diagonal response here, but in between, the signal propagates in the wireless medium. So you have a full matrix, full interlayer propagation matrix. So this product of matrices gives you a non-diagonal structure. So you are mimicking a non-diagonal structure through the use of a cascade of diagonal structures. Of course, there are pros and cons, because the more the layers, the more the losses. I mean, you can get a gain, but at some point the losses start kicking in. So there is a trade-off as always. Okay, but this is a way to split a complex task into simpler tasks. Okay, simpler implementation. And then the most exciting to me is really to view this multi-layer device as a computing platform, so a platform that can do complex operations. And there are quite a few. There is a lot of interest in the mathematical community in building devices that can do some mathematical operations. Now, one example in a paper that we also wrote with Chao is to use this multi-layer surface as a device to estimate the direction of arrival of a signal by computing the DFT when the signal goes through this device, and from the DFT we could retrieve the angle of arrival without using any phase information, but only through power measurements, and we got quite good results on that. So it's not only beamforming or change the direction of the signals, but you can really do quite complex functions, including a DFT. Okay. So, and then the bottom line is that we have seen that whether it's communications or whether it's sensing, by adding layers, and if we optimize the structure, we could get some gains. That's essentially the bottom line. Even though the fundamental limits are not understood yet, and even though the models that we have been utilizing so far are relatively simple, so they still don't fulfill the electromagnetic signal information theory paradigm, are still relatively simple. So now, this is the paper published at ICC, if you are interested, and this is, on the other end, a paper that shows a platform which is very, very simple, which is done with a group led by Professor Q here. in China. So I just show you the proof of concept, and then I just conclude. So this is the testbed. So the testbed is a 2 or 3 layer device where we have a sort of transmit arrays where each unit cell is a binary unit cell. So you can only change the phase of 0, 180 degrees, and it operates at sub 6. Okay. So the colleagues in China, they run some experiments through this platform, and in terms of communication performance and sensing performance, so estimating the direction of arrival of the signal. And you can see that the obtained results show that with this hardware, increasing the layers, you can get a better received power, or you can reduce the error in terms of angle estimation. Okay, so it's pretty promising, even though the algorithms that are utilized are relatively simple compared to what we can find in other papers. So there is still a gap between theory and experiments, but we are trying to close this gap. So now, in 1 minute, 2 interesting directions in my opinion. So one of the key point here is that if you go back here, for example, these layers, now people don't really optimize, for example, the locations of these layers, or they don't really optimize the shape of the surface that could also be optimized. So now there is an interest in what is called flexible intelligent metasurfaces or conformal metasurfaces, which are basically metasurfaces that you can bend a little bit, or where you can optimize the positions of the antenna elements. It's also related to the concept of fluid antenna elements or to movable antenna elements. Okay. So now I don't have much time, so I just want to show you that if you could not only optimize the risk configuration, but also the layout, okay, optimizing the positions of the unit cells, you could get some gains. For example, this for a planar deployment, you could get some gains in terms of SNR, okay, which is not negligible at all, okay. And another interesting point is to add to these surfaces the sensing capabilities in an autonomous way. And here there is a concept that is known in the field of metamaterials, but has not been studied that much in the field of wireless communication, which is the concept of space-time coding metasurfaces. Yeah. So this is one of the recent papers that we published on this topic, and the idea is essentially the following. So we could have a surface where we not only control the phase of each element, the phase shift introduced by each element, but we control the phase shift over time through a periodic function. And this periodic function has this, what it does. This periodic function allows us to change the scattering pattern of this device when the signal illuminates it in a way that we have the signal for communications, and plus we have different harmonics. So we have the signal that can go in different frequencies, basically. And if we are, and depending on the angle that illuminates the signal, we can have different frequencies. So if we are able to match the direction of arrival with these frequencies, we could try to infer the direction of arrival from the scattering pattern. And that's essentially the idea that there is behind that. And this could be done in an autonomous way, in the sense that the signal illuminates the structure, and then we could build a machine learning device that allows us to understand basically this from the radiation patterns. So I'm not gonna go more into the details. I just wanna wrap up by saying that I mean, there have been a lot of work in terms of reconfigurable metasurfaces. Most of them are reflecting surfaces that have been studied, or also star arrays. And now, I mean, people are looking at how we can do more processing, enhance the processing capabilities by having these multi-layers, and also how we can add multiple functions, not only for communication, sensing. And so these technologies, SIM, FIM, and space-time coding metasurfaces could be promising solutions to study and to understand basically the pros and cons. Okay. So with this, I think that I stop because I utilized all my time. So I thank you once again for having me. I mean, if there are questions, maybe time does not allow, but these are my emails, so feel free to get in touch. Thank you very much.
Thank you very much, Marco, for your presentation. I see that we have one question. Someone was telling me that the chat is the function is disabled, so please use the Q&A section in our webinar. But there is a question from the audience regarding multi-layer RIS structure for realizing beamforming in analog domain. How do you feed in the signal to be beamformed? Does feeding signal and RIS weights needs to be jointly designed?
Yes. So you mean this? Okay. Yes. Absolutely. Yes. So the where it is? Yes. So this structure here. Yes, absolutely. Basically, what you do, you need to optimize joint. You need basically to optimize the transmission coefficient of each basically of the elements that is on each of these layers. Of course, I mean, you can also try to, if you have these holographic implementations with the feeders that are co-located on the first layers, you could also try to appropriately shape basically the input signal that is here. But in general, you need to optimize this jointly, both the signals that illuminates the first layer and then how the signal propagates through the layers according to the locations of the users. Absolutely, yes.
Okay, thank you very much. If we don't have any other question, there is a question in the Q&A. But actually, I would say, Marco, that you can reply directly here in the Q&A sections, since we are behind schedule. And I will give the floor to Chuan Nguyen now for his presentation. Thank you very much.
Thanks.
Yeah, thanks everyone. Can you see my slide?
Yes, we can see it.
Okay. Yeah, okay, thanks everyone. I'm Chao here from NTU, Nanyang Technological University, Singapore. So thanks for the organizer to invite me to have this chance to present our recent work. So my presentation is quite different from the previous two. Okay, so I'm going to talk about this so-called Rybert atomic quantum receiver. Okay, short form the RAQR. Okay, and what is the equivalent signal models for wireless communications and sensing? So these are joint work with my colleagues from NTU and also from Samsung, is from the DSO, is the Defense Organization in Singapore, and the Debuff from Khalifa and Hanjos from Southampton. Okay, this is the outline. So I'll first give an introduction about this so-called quantum things. Then I will talk about these quantum sensors. Okay, what is the so-called signal models and some results to support the results, and also discuss about the future topics. Okay, so this is the brief history about the so-called quantum mechanics. Because just nice that this year 2025 is happened to be the 100th anniversary. For the first paper, they talk about the modern quantum mechanism. So over here, you can see a lot of the famous physicians. Okay, they've been contributed a lot to this area. And typically for the quantum, right, there are these three main pillars. Okay, one is the quantum computing. Okay, which we heard a lot. The Googles, their quantum computing, the breakthrough, etc. And the other one that is quite well established is about the quantum communications, where we have the QKD, the key distribution, etc., for secure communications. And today our focus is on the quantum sensing, which means that we use the quantum atom as a sensor. Okay, so typically there are four kind of enablers technologies for the quantum sensing. Okay, for example, we have the superconducting, trapped ions, solid state spins, and also the neutral atoms. And for today's our talk is mainly focusing on this type of neutral atoms type of quantum sensors. Okay, which is based on the so-called Rybert atomic sensors. Okay, why is that so? Let me explain to you in the next slide. Over here, these are some of the applications that this Rybert atomic sensors has shown. It has provide application in these areas. For example, it can be used in wireless or satellite communications, used in the radar or remote sensing, localization as well, imaging, and navigation without the GPS, EM, electromagnetic field probe, and very high precise time and frequency synchronization, gravity detection, and radio astronomy. Okay, so that's why in this talk, right, we are focusing on this so-called Ripple atomic quantum receiver. And why we need to look into this thing? So if we look at this diagram, right, this is the so-called very classical radio frequency receivers. So with these antennas here, then go through some filter, and then this LNA, the low noise amplifiers. Then over here we have the local oscillator comes in, then we have the mixer, and then after that go to the analog to digital. Okay. So for such classical RF, the receivers, right, there are some limitations. First of all, it has limited sensitivity, mainly restricted by the law of physics, for example, the thermal noise. And also the antennas, right, we rely heavily on the well-calibrated antennas. And with these chicken and egg problems, because how we going to calibrate the antenna, you know, there must be something that is accurate enough such that we can calibrate this antenna to make sure that the response is correct. But how we get the first accurate things coming out first? Then second is that this rely on some complex circuits for the down conversion as well. And so all these things are power hungry, especially when we go for multiple antennas, so on and so forth. And that's why we are going to look into this so-called Ripple atomic quantum receivers. So it looks something like this. We are going to this structure later on in more details. But mainly what we can see is this. For this type of sensors, right, there are these distinct features. First of all, is high sensitivity. Okay, so there's this thing called the standard quantum limit, SQL. So this SQL has demonstrated a very high sensitivity. Okay, even though in today's technology, maybe we can't achieve this SQL yet, but at least this limit gives us a very good vision that, you know, how sensitive this device it can achieve. Second, this device has a broadband tunability capability. From DC all the way to terahertz, these sensors, we can tune it to achieve any frequency that we want within this range. Next, this thing is very small in size, so it has a compact form factor. Okay, so this allows us to have a receivers, even the frequency is very low. And most importantly, like we say just now, is the chicken egg problem. This one with this so-called standard unit SI traceability. So without the calibration, we can know that this thing detects exactly what frequency. So in the literature, which we shown over here on the lower left-hand corner, people have demonstrated these sensors has such capability. For example, we can detect amplitude, phase, and polarization. And it can have a multi or continuous band detection. It can also have a spatial displacement and direction detection. So all these things, people in physics, they have done some experiment that has shown that these sensors have such capability. Okay, so next we'll introduce these sensors in slightly more details. Okay, so if you look at this diagram at the top right, this is the standard atoms, okay, the normal atoms where we have proton, neutron, and electrons. However, for the Ripple atoms, right, it means that one of the electron is get excited to a so-called very high energy or high energy state. Okay, so you can see that this electron is the orbit is slightly larger or higher than the others. Okay, so this is what we mean by the Ripple state. Okay, so this Ripple atom is an atom with one or more electrons that have very high principal quantum numbers. Okay, and this excited state, right, making these atoms, right, very sensitive to the electromagnetic field sensing. Okay, so your response to the EM wave sensitivity. Okay, so let's look into in more details. Okay, so this is how a typical Ripple atom sensors receiver looks like. Okay, so over here you can see this is a cell. We call this thing a cell. So inside this cell there are many atoms is inside. Okay, so how many atoms inside? The density is one parameters we need to optimize. Okay, inside these cells, right, you can see some are the blue color atoms, which are the ground state atoms. Okay, but some of them, the purple dots one, this is what we mean by the Ripple atom. Okay, so how they become the Ripple atoms is because they get excited by the laser beams. Okay, so there are two laser beams over here. One is this red color is the probe beams, Okay, the other one is the blue color, the coupling beams. Okay, and these two laser beams, they are pointing to different directions. Okay, one from the left to right, the other one will be from the right to left. Okay, and after that, these probe beams will be detected by this photo detector. Okay, at the end. Okay, so let's see how it works. So for the atoms at the ground state, right? Okay, so you can see their energy is over here. Okay, but when we put in the probe beams, the red color, the laser, will bring out the energy of the electrons to the so-called excited state. Okay. However, when we put in another the laser beam, the coupling beam, it will bring this excited state to a higher level, which is what we call the ripple state. Okay, so the electron will be excited at this level here. Okay, later on when the electromagnetic wave pass through, okay, comes in, then these atoms will impacted by this electromagnetic EM wave, then there will be some reaction. Okay, and then the reaction will be detected by this photo detector here. Okay, when the change in the laser beams. So the reaction is what we call the EIT, electromagnetic induced transparency. Okay, so over here you can see when we observe from the PD, right? If just the probe laser, this is how it looks like. Okay, when we have the coupling beams, then this is the probe and couplings. This is what we observe. Okay, and all this is observed without the RF signal yet. Okay, without the RF signal coming, this is what we observe. So what happens next if there are some RF signals? Okay, so over here we show you two structures. Okay, the first one is called the LO3. Okay, LO stands for the local oscillator. So in this case means that there's no LO. Okay, no LO. This is the so-called standard structure. So over here, this is the cell that we see just now. Then the blue and red, the laser beams. Then this is the photo detector. So whenever there's a RF signals comes in, okay, for these LO3 structures, we can only detect the amplitude. Okay, we can't detect the phase of the RF signal. Okay, but when there's a RF signals comes in, we'll have this so-called ATS. Okay, this outer tonal split. Okay, which means that based on the output you observe here, when the beams get split, right, how wide this beam being split, this will tell us the amplitude of the RF signals. Okay, that's how we can detect the amplitude. Okay, and for this structure, right, we need to scan a laser frequency to obtain this ATS peak. The other structures that is also commonly found in the literature is so-called the LO-DRES, which means they come with a local oscillator. Okay, it's called a super heterodyne structure. And over here, when we're shining an LO, and then when the RF signals comes in, okay, then we can detect something over here. And in this case, right, what we get is a amplitude more amplitude more is modulated signals. Okay, so this case, we can detect both the amplitude and phase of these RF signals. Okay, we can detect both the amplitude and phase. So it's like the normal antenna, RF antenna that we have. Okay, now we can detect what is this RF signal and what is the phase. Just that instead of using the antenna, we are using this ripple atomic receiver. Okay, so this one we are not relying on the AATS anymore. Okay, but we explore the so-called bit nodes of the optical signals for us to recover back the amplitude and phase of these RF signals. So there are some survey kind of papers that talks about these ripple atomic sensors, with one just accepted in the WCM Wireless Communication magazine recently, a few months ago. So there are some others, mainly from the physics point of view. So the difference from us is that we try to translate, what people in the physics to a language there where the communication engineers there we can understand. Okay, so next we are going to tell you, what we have done about the signal modeling. Okay, we try to use mathematics equations to model this receiver. Okay, once we have the receive signals, like for example, y equal to hs plus noise, then we can design whatever the communication, MIMO, or sensing. Okay, then we can use it for wireless communication and sensing. Okay, so there are some works that have been done in the literature. Okay, in fact, quite a lot, and many of them are in the physics domain. Okay, so for example, people who have been trying to improve the sensitivity of these sensors, And people have been looking at the so-called multi-band reception or continuous band reception, or how we can detect the amplitude, phase, polarization, modulation, so on and so forth. Okay, and then there are some verification as well. Okay, so these are the literature that we can find in the literature, and you can get this from our magazine, the paper. However, from this literature, right, there are something is missing, in the sense that they didn't tell us what is the signal models, the mathematics equation, okay, that can describe such receiver. Okay, and this signal model is important because for us doing the wireless comms, for us to derive the signal to noise ratio, the capacity, to design the beamforming scheme, we do need this signal model. Okay, so that's why in this talk, right, we are going to fill in this gap. Okay, we try to derive the end-to-end the reception scheme, and then we try to construct the equivalent baseband signal model that we can use it for wireless comms and sensing. Okay, this is the how it looks like. Okay, so over here is a seesaw, single transmit and single receiver. Okay, single input, single output. So on the left hand side, this is the transmitter. Okay, the transmitter then go through the channel here. Then the right hand side, the blue color box is the receiver. Okay, whereas over here we're going to replace the traditional antennas using the Rybert atomic receiver. Okay, so this is what we are trying to do. Okay, so for the Rybert atomic quantum, the receivers, right? So this is the receiver structure that we propose. Okay, over here you can see we divide into 5 different steps. Okay, the first one is the atom itself, the sensing, the atom sensing. Then next is the photo detection, because whatever detection is captured through the light signal using this photo detector. Okay, after that, this will go through the LNA. Then we'll do the down conversion going to the baseband. Okay, then do the sampling, then we can do whatever signal processing that we want. Okay, so we try to see when we replace this receiver with the Rybert atoms, how the baseband signal will looks like. Okay, so this is what we try to do. Okay, if you look at the first 2 parts, right, the Rybert, the sensing part, and the photo, the detection. Okay, over here you can see we have 2 laser beams, the probe beams and the coupling beams, the blue and red laser. Okay, and this XT is the incoming signals. Okay, incoming signal. And in this paper, right, we are just looking at the headline system, which means the system with the LO. Okay, so the LO will comes in. Okay, then with this, whatever signals here will be detected by the photo detector. Okay, and over here in this talk, I was just focusing on this direct incoherent optical detection DIOD schemes. There are multiple schemes as well, okay, which is described in the paper. But for simplicity, we're just focusing on this DIOD scheme. Okay, the output signal over here, right, at this point, after the LNA and photo detector, it looks something like this. Okay, this is the signal that we will observe over here. So it looks complicated, but actually it's not. Okay, you can see there are two parts here. The first part here, this one is the LO dependent, so it is a DC signal. Okay, so this one later we can get filtered away quite easily. Okay, then this purple part, right, is the RF signal, our signal that we want to detect dependent, and it's a AC signals. Okay, which is this part in the purple here. And inside this purple part, again, there are 2 different parts. One is the atomic response linked to the atomic receivers. The other one is the RF signal that we want to detect. Okay, so we will try to process this purple part. Okay, so for this part, after we will go through the down conversion, sampling, and signal processing. Okay, so over here, the input here will be this signal here, is what we show. Okay, and after the low pass filter, which is here, okay, we can filter away the DC signal. So we left only the purple part. Okay, and eventually at the baseband, right, after some derivation, okay, we can express it in a simple expression, looks like this. Okay, so over here you can see it's very similar to the traditional signals that we receive using the antennas. Okay, at first you can see at the right hand side, this is the noise. the AWGN noise, okay? The noise that is the noise. Then this SB here is the transmit signal, the RF signal that we want to detect, the baseband signal of the RF signal that we want to detect. Then this H is the wireless channel, okay, as per normal. Okay, something new is these two things here, okay? One is the phase shift, okay? And this phase shift is the one that introduced by these Ribert atoms. So this is quite different from the traditional antenna system. Traditional antenna system, we don't introduce a phase shift, okay? But whereas for this Ribert atom, this phase shift is introduced. So this makes the difference compared to the antenna. So when you form an array or you do the DOA, etc., this phase we do need to pay attention. Okay. Next is that this Ribert sensor, right, also introduce a gain, okay, a power gain. Okay, that's why it makes it more sensitive. Okay, so let's look at the results. How accurate is our expression here compared to the actual case? Okay, because when we I skip some steps. Okay, because when we derive this equation, we make some approximation. Okay, and then to make the expression more neat, there are some approximation done. So we need to check how well is our model looks like. Okay, so these are the parameters that we use in the simulation. Okay, so for these atoms, right, there are quite a number of parameters that we need to set. Okay, for example, atomic density is like within this cell, how many atoms they are. Okay, so this is the density. Then the wavelength, there are two wavelengths, the probe and doubling. What kind of radio frequency that we use for the, what's the frequency for the laser beams? Okay, so for all these parameters, right, we have obtained it from the physics, the papers. Okay, so all you need, you can refer to the papers, then you can use these parameters to use it for your simulations. Okay, so these parameters we have verified, and then these are commonly used by the physics people. Okay, so this is how it looks like. Okay, so over here you can see the purple line is the exact waveform. Okay, and then the blue dotted one is the one that we approximate. Okay, so we can see they are quite well aligned. Okay, for the both cases. Okay, which means that our expression that you see just now quite aligned with the exact case. Okay, there's some small error which I'll show you next. Okay, over here you can see this is the RF signal power. The radio signal powers that coming in. And then this is the PD output, the photo detector, the output. Okay, so over here, you can see there are two versions. One is the non-linear, one is the linear, the approximation. So what you can see is this. Over here, this whole region, right? Okay, the linear approximation that we use, right, they match quite well. Okay, but there are certain parts, right, certain region, okay, the sensor will have this non-linear behavior. Okay, so of course, during this region, this non-linearity, we can't approximate using linear approximation. Okay, so this portion we can't approximate well, but over here, the whole section, our linear approximation makes quite well. Okay, and of course, you take note on this non-linear portion because this is something that that later on when we design the beamforming, etc., we do need to take care of this non-linearity as well. Okay, so it's some research problem that we can address. Okay, over here you can see is the approximation error, okay, for our schemes. So you can see most of the case, right? For most reason, you can see the error is quite small. It's like the 10 to the power of minus 10. Okay, so this again confirm that our expression is matching quite well. Okay, the error is very small. Okay, so as conclusion, right? Okay, over here, what we show you is that we propose an end-to-end receiver structures using this Ribert atomic, the receiver, the atom structure. Okay, we come up with the corresponding baseband mathematics signal models. We try to make it as familiar to us as possible. Y equal to HS plus noise. Okay, and our result is quite matching quite well. Okay, especially certain region, the region we're matching quite well. Okay, so with this model, right, then we can use it for many applications. For example, we can analyze the performance. Okay, for example, what is the SNR, what is the capacity, so on and so forth. And more importantly, with these models, right, it helps us to optimize later on for the atom sensor as well. Because there are a lot of parameters. That is just like what you see, the frequency of laser beams, the atom density, etc. All these parameters, when they do experiment, they need to optimize. Okay, but with our expression, we can help you to optimize these parameters before you do the experiment. So that helps you to quickly optimize the parameters. Okay, so in terms of future works, okay, so there are quite a lot of things we can do. So for example, there are some impairments that we have not modeled them well yet. Okay, right now what you see, we assume everything is perfect. Okay, but in real world, there are some impairments. So these are things that we need to take care. Okay, and then just now we mentioned about the nonlinearity. Okay, certain part of it is nonlinearity, and this thing we need to fit it well as well. Okay, right now we can't do it yet. And of course, how we can reach the so-called SQL limit. Okay, these are something that even the people in physics, they are trying to do. Okay, for the communication, the people, right, we can optimize the parameters so that how we can achieve the best performance for communication and sensing. Okay, and then how we can extend it to wideband scenarios. Okay, and then we can use it for satellite comms or for ESIT as well. Okay, so these are many things that we can do. We published some papers. Okay, one is the magazine paper that I mentioned to you is just accepted. I think should be in the early access already, if not in the archive. The one I presented, we just reported recently in the conference QCNC this year, I think 2 months ago in Japan. Okay, the journal of it, we are in the revision now. Okay, you can find the archive online. Then with another paper also on Seesaw, also on archive as well. We are trying to extend it to MIMO as well. And this one will appear in the IICC June this year. Then we have also applied it for the DOA to find the direction of arrival. Yeah, that's all for my presentation. Thanks, Gil.
Thank you very much for your presentation. I see that we have 2 questions in the Q&A section. I would ask you only one, and then for the other one, you can reply directly there because, as I mentioned, we are behind schedule. For example, it was just a question here. How is the noise performance / noise factor based receivers comparable to conventional receivers? So if you want to take that question to answer it now, and then for the others, you can answer live in the Q&A section.
Yes. Okay. So the traditional receiver, we only consider the thermal noise. Okay. But for the right sensors, if I'm not wrong, there are 4 types of noise. Okay, there are quite a lot of noise. So I can't remember exactly what are those noises. You can look at the magazine paper that we published. Okay, in the magazine paper, we list down all the noises. There are 4 or 5 of them because the atom itself, there are sensors, there are noise. The photo detector, there are noise. The laser beam, there are noise as well. So quite a lot of noise in this system.
Thank you very much for your answer. Then, as a reminder, just check the Q&A section for the others too, and please answer to all the other participants. Also, the same is valid for Marco because he has also some question after his presentation. And I would just like to give the floor now to Davide Dardari, full professor at University of Bologna, for his presentation. Davide, you have the floor.
Good afternoon to you. Thank you. Let me share the screen. Okay. Can you see the screen?
Yes, perfect.
Okay, perfect. Okay. Okay, so thank you first for the invitation. So I'm from the University of Bologna, Guglielmo Marconi department, and also I'm affiliated to the CNIT National Laboratory of Wireless Communication in Italy. So today I'm talking about multifunctional electromagnetic signal processing using dynamic scattering arrays. Well, so you know that one of the key aspects of CG will be the fusion of the digital, the physical world. So that means most of the data sources will not come from people, but from humans, but from things. So that we expect an explosion of the traffic demand, but also new applications such as digital twinning, extended reality, and so on. But at the same time, we have a lot of constraints to deal with. So the energy constraints, bandwidth, reliability, latency, just to mention some. So among the different solution technology that has been studied in the last years, for sure, one option is to increase a lot the number of antennas so that to exploit the spatial multiplexing capability. So leading to the extremely large antenna arrays, actual XL MIMO system. So we will assist an explosion of a number of elements in antenna arrays, so that just to at least increase the capacity of the system, but also, as also Marco mentioned before in his presentation, if we go large, so if we have relatively large antennas, so we can also exploit the near field region. So it is likely that even in practical scenarios, users will be located in the near field region of the antenna array, so that we can exploit some peculiarities of the near field propagation, such as beam focusing, high rank loss communication, single antenna positioning, exploiting the wavefront, the curvature, and so on and so forth. So, but the problem is the digital bottleneck. So, what is the meaning of this? So, you know that after the publication of the Shannon landmark paper in 1948, so the digital revolution rapidly accelerated, and so shifting the processing, information processing from the analog domain to the digital domain. So today, the exponential growth in digital computing capabilities has pushed the boundary between the digital and the analog digital processing in wireless system closer and closer to the antenna, for instance, exploiting software-defined radio. But as long as we want to realize very large antenna arrays, so system exploiting very large antenna arrays, so at a certain point, we even using hybrid implementation, especially if we work at the high frequencies, the system could not be scalable in terms of power consumption, latency, and size. So this is what is called somehow the digital bottleneck. So that we might have sustainability and scalability issues in future wireless network. So that one possibility, which is the main topic of this today, is shifting part of the processing to the electromagnetic domain, so that by balancing what is done in the digital to analog in order to say reduce the latency, reduce the energy consumption. So this is what is called wave-based signal processing or over-the-air electromagnetic signal processing. So several names more or less to indicate the same thing. Well, so today we'd like to focus on what I call the over-the-air electromagnetic signal processing using reconfigurable scatterers. Let me take the pointer. Okay, so what is the meaning of this? The meaning is that we, as a general setting, we supposed to have electromagnetic processing structure, which is composed of a lot of a huge number of passive, possibly lossless, reconfigurable scatterers that interact each other in the reactive near field, so that we can, by playing with the parameter theta, so the vector of theta containing the parameter, we can play with, then we can change the way these scatterers interact with each other and interact with the impinging electromagnetic wave, with the purpose to modify, to transform the electromagnetic wave according to some desired results. So basically, we can the main obviously purpose is to have a very high energy efficient structure. Basically, we have almost zero latency because everything takes place at the speed of light and low complexity. So we can imagine two scenarios. We can classify this electromagnetic signal processing in two scenarios. One scenario is this one, in which we suppose to have active sources, for instance, a transmitting antenna or several users transmitting whatever, and located in the near or far radiative field, so far away from the sources, we have one or more electromagnetic structure composed of reconfigurable scatterers. And then we have a receiver space. So receiver space here is indicated as one space, but it could be composed of several disjoint spaces, for instance, of several users. So the idea here is to use this structure in order to shape the propagation environment and then obtain some desired result at the receiver space. And so this is and within this class of let's say structure, so we find the reconfigurable intelligent surfaces that were mentioned before by Marco, metaprism, self-communicating meta surfaces. So this is quite well investigated topic. But there is another let's say scenario in which we move the sources very, very close to this electromagnetic structure, in particular in the directly near field, so that mutual coupling takes place between all the elements, included those active. So this can be a typical scenario in which this structure is adopted in a base station or in the access point, with the purpose to reduce the complexity, to reduce the energy consumption, and in particular by reducing the number of RF chain, because typically to each active source we have attached an RF chain, which is one of the most, let's say, energy consuming part of the transmission system. And within this class, we find several technology solutions, such as electrically steerable passive array radiators, stack intelligent metal surface that were addressed before by Marco, dynamic metal surface antenna, and so on and so forth. So today we focus on this, on this particular scenario. And but I would like to mention that the idea is not very new, because the main idea of let's say considering one active element surrounded by passive antenna elements with reconfigurable reactive loads dates back to the 1978 in a famous paper by Roger Harrington. At that time, the purpose was to configure these scattering elements in such a way we can shape the radiation diagram by using just one active element. So this idea has been, let's say, extended. Has been in even the recent years, and today this structure is called ESPAR, so electrical steerable passive array radiator. But it could be interesting to generalize this towards what I call the multifunctional electromagnetic signal processing. So what is the idea? The idea is that, so we have this electromagnetic structure, we have several active sources, and typically the number of active sources is much less than the number of scattering elements, so that we can have even a huge, let's say, device. And the idea is the following. So we would like to obtain a desired electromagnetic field response observed in the receiver space by properly designing the parameters of the electromagnetic structure in such a way the observed electrical field is a linear combination of the inputs x1, x2, xna, whereas each input let's say provides an ad hoc, a dedicated, let's say, response, so f1, f2 as a function of the space, but we using the same configuration. So the problem is finding the configuration theta, so that with the same configuration the signal emitted by active source x1 give rise to a certain response here, whereas the signal transmitted by a second active source give rise to a different function, and so on and so forth. So I would like to obtain this kind of multifunctional electromagnetic signal processing, exploiting the interaction in the near field here. Well, so a possible way to do that is to generalize the concept of ESPAR, and to some extent also the concept of SIM, by considering a very general framework in which we're supposed to have up to NA data stream, an optional baseband digital processing that processes only a few streams. Then we have associated with this NA RF chain, and the output of each RF chain feed an active element, so an antenna, basically. And we suppose that these few active antennas are surrounded by a large number of dynamic scattering array that are the reconfigurable scattering elements. So the structure can be two-dimensional, could be three-dimensional, whatever, so very general structure. But here the idea is that we, through the interaction between the near field between all these elements, we jointly obtain both the electromagnetic processing and the radiation. So all these elements contribute to the radiation, which is not the same as happened in SIM, for instance, where only the last layer radiates. So this is the more detail about the modeling, but I will skip some of them. So we can model each scatterer as an antenna with a configurable load. Ideally, it would be nice to have a reactive load so that we don't have power consumption, but later we show a more realistic model. And then it is possible to derive, for instance, the antenna input impedance by some circuit level derivations. I would like to mention that all these matrices don't depend on the configuration, so this can be computed offline, starting from analytical model or from electromagnetic level model once we fix the technology we use to build this element, and once the geometry is known. So this can be done offline, and then the effect of the parameters takes place according to this expression. So we have an input impedance that depends on the way we configure the scattering arrays, so that if we want to ensure that we have a maximum power transfer between the RF chain to the DSA, as initial simplified model, we can assume that we have a lossless ideal matching network, so that this ideal matching network. The main drawback of this is that since the matching network depends on the input impedance, and the input impedance in turn depends on the parameter, so that means we need a reconfigurable power matching network. At the end, we show that it is possible to remove this without a significant performance loss. And then finally, we have an optional, the baseband, this is the processing that can be modeled by this matrix, and this normalization has been put in order to have the transmitted power equal to the power of the vector x, as done typically in signal processing. Well, skipping the details, so it is possible to derive a relationship between the input vector x and the total currents that flow both in the active and passive elements of the DSA. So this is the expression, so that this term accounts for the electromagnetic processing. So we can tune the electromagnetic processing by setting proper value for this vector or the parameters, and this is the digital processing, if any. Well, so then we can derive the end-to-end model, because this obviously is the current, so this is not what is seen at the receiver. So then with the purpose to derive an end-to-end model, so a model starting from the input symbol to what is observed by the end users and the antennas. So we can embed also the channel, so that we can define, for instance, a generic test points, observation point, and the vector y. And then once we know the propagation scenario, it is possible to relate the currents flowing here to y by defining the transimpedance matrix of the radio channel. So in the free space, this can be computed easily analytically. In case we are not in free space, this comes from any model. And so that this is the final end-to-end model, which depends the parameter theta, depends on the digital, let's say, processing. So that the problem is to find, this parameter in such a way we get the desired end-to-end channel response. In particular, since we, as I mentioned at the beginning, we want to obtain a multifunctional response. So, for instance, we can define a target end-to-end vector for each input signal. For instance, H1 denotes the channel response between X1 and the observation vector Y. H2 indicates the end-to-end channel relationship between the X2 and the observed vector, and so on and so forth. So we collect all these desired response in this matrix. So at the end, the problem is to find the data, the WD, in such a way the total end-to-end channel gets close to the H of OPT with a constraint on this constraint on the power, basically. Okay, I'll skip the details of the optimization. So this is not simple optimization problem. So it can be solved, for instance, using an alternate approach, but due to the lack of time, I skip this. Let me show some example. So just to understand what can be could be the potential of this kind of structure. So in this example, I consider just a very simple DSA. So it's a 2-dimensional DSA, a sort of disk with a disk shape in which we have 5 rings. And in these 5 rings, we deployed the scatterers with the lambda 4 spacing. Lambda 4 over 4 is a sort of magic number. Okay, so it's sort of optimal number which provide the best performance with respect to other choices between the spacing. And here in this example, we have 121 scatterers, so that at 28 gigahertz, the total size of this is just 3.2 centimeters. So here we have just one RF chain, so we have just one input. So we have only one active antenna. So this is very similar to the SPAR case, but with the difference that we have more, let's say, rings instead of one. And here the results. So here, this DSA has been designed in such a way to obtain different beamforming to different angles. And as you can see, the radiation diagram are very, very nice. In particular, the shape doesn't depend on the angle, thanks to the circular structure. But as you can note, the gain is quite high, and it is interesting to compare this gain with the gain we would obtain using a conventional uniform linear array. We having the same aperture, so with the same aperture of 3.2 centimeters. So that means 6 elements, active elements, and this is the classical, radiation diagram, which depends on the angle. So the best one is in the direction of 0 degree, but the worst one is 90 degree. Or comparing this with the uniform circular array, classical uniform circular array, but in this case we need 36 active antenna elements to get the same aperture, and this is the response. So if we compare all these diagrams, what we can see is that here we get a much higher gain with respect to, especially with respect to this one, but also with respect to the UCA. So basically what we obtain is a super directivity effect. And we obtain a super directivity effect in all directions. You know that typically super directivity effect can be obtained by coupling the antenna, but only in the end-fire direction, not in all directions. So here we obtain the super directivity effect in all directions with a very simple structure. I skipped the second example due to the lack of time, but just to show that here we can have a multifunctional, so different beamforming, parallel beamforming to different users, so using zero forcing. So basically we can associate a different radiation diagram in parallel to 4 users using the same structure. Let me just focus on the last example in which we have the same simple disc shape DSA. But now we have 4 active antennas because we're supposed to have a multiple channel with a rank 4. So you know that from MIMO theory, if the rank is 4, we can obtain a spatial multiplexing of 4, so with 4 layers. So in order to exploit it, what we need to do at the transmitter is to have a precoding. So typical precoding is performed in the digital domain by means of matrix multiplication, which might have some complexity. Instead, here we propose to do it in the electromagnetic way. So we designed the DSA in such a way the overall effect of this DSA is equivalent to the precoding matrix. So this can be done assuming that we perform the classical single value decomposition. So, and by setting the target, let's say, processing at the electromagnetic level equal to the precoding, the desired precoding matrix. Well, so this is the result. So as what you can see here is the obtained, let's say, diagonalized channel. So lambda hat. So ideally here we would have a diagonal matrix. Obviously, this is not ideal. So here instead of having minus infinity, we have some different numbers, but these are in dB. So that means the off-diagonal elements are not 0, but are very close to 0. So that means the channel is almost perfectly diagonalized. So that means the electromagnetic precoder works very well. Obviously, this is ideal. So here below you see what happens if we consider some implementation error. So and then you can see that until the error is close to the 10%, we can keep the coupling above minus 10 dB between the layers of the communication. Well, but all these results have been obtained considering a perfect power matching network, which is very difficult to be implemented, especially if the number of RF chain is larger. So that it is possible to remove completely the matching network by inserting reconfigurable loads here. So we remove this, and then let's say considering a sort of joint matching DSA optimization. So basically we optimize both the load of the scattering elements, but also the impedance, which is in parallel to in series to the each active elements. And then by means of this optimization, it is possible to obtain almost perfect power matching without a dedicated network. And also, latest results have been obtained by considering more realistic, let's say, configurable load, in particular using Varactor diodo. This is the typical model for Varactor diodo. So that here we have also some dissipation. And then, but numerical, very, let's say, recent results have shown that we have almost negligible approximation loss with respect to the perfect matching and loading shown you before. Obviously, the main drawback is that we have some reduction in the array efficiency, which is about 70%, 80%, because of not perfect matching and because of the dissipation in this. But this is more realistic model. Well, so last comment is on comparison with respect to the SIM. So actually, the DSA can be also seen as a generalization of the SIM. So it's just a matter of determine which element is coupled which one. Here we consider a general coupling, but if we limit this, we can also model the SIM in this case. But as I anticipated at the beginning, the main difference with respect to the SIM is that the stack intelligent metal surface is that in the stack intelligent metal surface only the last layer radiates. So all the intermediate layers contribute to the processing, as Marco Di Renzo showed before, but only the last layer radiates. So this puts some limitations on the flexibility we can, let's say, generate the signal. Whereas here, all the elements contribute to radiation, so that we have more flexibility, and in particular, we can obtain a similar performance with a more compact structure. Obviously, the main advantage of SIM is that we can exploit let's say, the similarities with the deep neural network, as Marco outlined before, so that, for instance, we can exploit feedback optimization algorithms like deep neural network, whereas here the optimization is much more complicated, so that is still an open issue to be investigated. So, conclusion, I presented a general framework to model, to characterize what is called here dynamic scattering arrays. So in a very general settings, and if we allow a global coupling in the near field of all the elements, so we expect a very nice flexibility in managing, in processing the electromagnetic field. And that obviously help in reducing the ref chains and then digital processing with a very energy efficient structure. What is currently under investigation is the analysis of frequency salary effects. So this is the recent paper on this. So the extension of also making the processing not only narrowband but also in wideband. So having a different let's say, function for different frequencies. So this can be obtained with the same structure. Then one open issue is the design more efficient optimization schemes. So because now they are mainly based on numerical optimization. Another problem which is similar to that explained before by Marco about SIMs is finding the best geometry, so the best placement of these scatter elements. So this is another problem, the combination with AI tools, and also we are working on also implementation of a prototype of this. So finally, this is the very last slide. Obviously, this kind of structures, both SIM and also DSA, cannot solve all the problems. So that it is very likely that in the future, what we will assist to is a combination of digital signal processing, analog signal processing, and electromagnetic signal processing. And the big question would be, well, what is the best trade-off? So for a given processing function, what is the best, let's say, splitting of the processing between the digital analog electromagnetic domain. So this is what is called a tree-hybrid architecture that has been, let's say, proposed by the group of Robert Heath. Well, so that concludes my talk. So thank you for attending, and open to questions.
Thank you very much, Davide. I see that we have a question from Malte Schellman. Is the DSA antenna already implemented today, or is it rather a theoretical study? What are the challenges for the implementation?
Yeah. Well, so thank you, Malte, for the question. Well, the very simple structure, so like SPAR has been already implemented today, but they're very simple. So that means, for instance, one active element and a circle of scattering elements. So you can find already implementation. In a more general setting, especially if we want to go three-dimensional, for what I know, there are no implementations. So that's why we are working with our colleagues, expert in antennas, in designing a prototype in order to validate experimentally this theoretical framework. Obviously, an intermediate step is to perform simulation at the electromagnetic level in order to validate the model. But for the time being, the model is quite accurate in the sense that it takes into account all the coupling, so that the only problem here, in order to get a good model, is to estimate the impedance matrix of the structure, so that once we have a good impedance model for the impedance matrix, then the rest is accurate. But so we are working on that.
Thank you very much for the answer. I see that there aren't any other questions for you, Davide, but I'm not sure if Marco is still with us. There were some questions for him. For example, can ESIT be extended to optical domain communication and free space optics and analog radio over fiber? Can you hear us, Marco?
Yeah, yes, I'm here. Yes, I'm here. So, I mean, electromagnetic signal information theory is, is a general framework of theory. So there is not one frequency where it could be applied, another frequency where it could not be applied. So certainly, I mean, all the times that we need to introduce more physically inspired or compliant models into our current models is certainly, I mean, an approach that could be leveraged. And then, I mean, also the corresponding signal processing algorithms that are based upon these models. Yeah.
Mm-hmm. Thank you very much. And there was also one other question for you. How many layers of the surface can be used without the need to amplify the transmitted signal? I think this was also for you.
Yeah, good point. So, I mean, so the choice about the number of layers is really a question mark because so all the simulation results that have been obtained are based on very simple models, at least those basically on paper. So based on these results, like David said, there are some magic numbers that are recurrent in these papers, and in the case of SIM, this magic numbers is 7. So it's not basically layers spaced lambda over 2 more or less. They basically, basically, if you have a given space, then you try to reduce increase the number of the number of layers. When you reach 7, you reach the optimum. Then you start getting something basically decreasing. Now, with the testbed, we obtain, so I cannot really tell you what the optimal number is. This is what based on simulation results with simple models. Based on experiments, this paper that I showed you, the situation is even trickier. Because we have seen that if the layers are not spaced sub-wavelength, we may even get worse results. Now this may be due to the not optimality of the algorithms that we utilized, because we did a little bit of brute force optimization when it comes to the test beds. But certainly, I mean, what is the best number of layers? It's really a question mark. Now, I mean, adding putting little amplifiers within the layers, I don't think that there are even results about that, because then we need to consider the impact of noise between the layers, and so whether this is amplified multiple times when the signal goes through the layers. So this is even more complicated. Yeah, so I guess that there is no general answer at the moment. But yeah, there is this magic number which is 7 under ideal assumptions. Let's put it this way. Yeah.
Thank you very much, Marco. And there is only one other question. I think this was addressed to Chao about does over-the-air computing via multi-layer SIM has the same issue with the accuracy like optical computing? I'm not sure if Chao can hear us.
I think this might be also to Marco, perhaps, because Marco, you discussed the over-the-air computing, right? During SIM, I guess.
Yeah, I mean, I can try to answer. Yes. So I think the question is whether there is a similarity with optical computing. Is this essentially the question? Let me read it again. I don't see if I can really. Okay. Does over-the-air computing with multi-layer are the same issue with accuracy like optical computing? So now the concept of, let's say this way, a SIM in the way that I presented it as well, is has been mostly studied in the optical domain. So are really the people who are doing optical computing that have been studying it, and there are indeed even more implementations in optics, where essentially these layers are layers of optical material, and then basically the signals propagates through them. So now I'm not sure exactly what by accuracy here it's meant. But I think that a multi-layer structure, whether in both ways we can interpret here in these questions, I think that there are close similarities. Now, I'm not sure exactly how by accuracy, what is the exact meaning of accuracy. But yeah, I think that the problems are similar. We are just utilizing a different frequencies and different technologies from the implementation point of view.
Great. Thank you very much.
Mhm.
I don't think we have any other questions. So we've come to the end of today's 16G Open Lecture. I want to express my gratitude to our speakers for their presentations. I would also like to thank everyone in the audience for your participation. All materials from today's lectures, including the recording, will be available on the 16G website. So please join us for the next open lecture that will happen in June, and we will announce the date shortly. On behalf of 16G, I wish you all a wonderful rest of the day and look forward to seeing you at our future event. Have a great day.
Thank you. Thanks, everyone.
Thank you. Bye-bye.
Ciao, ciao.